There's a planet at the edge of our solar system that most people will never see with their own eyes. You could stare up at the night sky for your entire life and never catch even a glimpse of it, not because it's hidden behind something or because it's impossibly far away, though it is both of those things. You couldn't see it because it's just too faint, too dim, too insignificant from our perspective here on Earth. That planet is Neptune, and 3 days ago it stopped behaving like any planet we've ever studied before. Let me set the scene for you. Imagine you've dedicated your entire career to understanding something, not just studied it for a year or two, but spent your entire professional life, maybe even your entire adult existence, focused on one single subject. You've written papers about it. You've trained other people to study it. You've sent spacecraft billions of kilometers through the void of space just to get a closer look at it. You've developed theories, written textbooks, built your entire reputation on understanding how this one thing works. And then, one morning you wake up to an email. It contains an image, just a simple image from a space telescope. And in that image, everything you thought you knew is wrong. That's not hyperbole. That's not me being dramatic for effect. That is literally what happened to Neptune astronomers around the world about 72 hours ago. The James Webb Space Telescope, the most powerful observatory humanity has ever sent into space, turned its golden mirror towards the outer edge of our solar system. It pointed its instruments at Neptune, a planet we last got a good look at way back in 1989, when a probe called Voyager 2 zipped past it at incredible speed. That was 36 years ago. That was the last time we had any real detailed information about what Neptune looks like up close. So when Webb sent back its first batch of infrared images, the astronomical community was ready for some interesting data, maybe some cool pictures, perhaps a few surprises. What they got instead was a complete and total reversal of what they thought they understood about how planets work. Here's where it gets weird. Are you ready for this? Because once I tell you these 4 things, you're going to want to keep watching until we figure out what's actually happening out there. First thing, Neptune's upper atmosphere has gotten radically colder. We're not talking about a few degrees of temperature change. We're talking about a drop so severe, so dramatic, that if the same thing happened to Earth, we would be in an ice age. We would be in catastrophic, civilization-ending conditions. And this happened in just 35 years. How is that even possible? The sun is barely visible from Neptune's perspective. It's like looking at a candle from a mile away. The planet is getting less sunlight than it did in 1989, not more. So how is it getting colder? Second thing, a ghostly green light show is happening across the planet's surface, but not where it should be happening. On Earth, auroras happen at the poles. They happen where our magnetic field is strongest, where solar particles get funneled down toward the magnetic poles. You go to Alaska, or Norway, or the Arctic, and you see the northern lights dancing across the sky. That makes sense. That's how magnetic fields work. But on Neptune, these auroras are showing up at the middle latitudes. It's as if the northern lights suddenly started happening above Miami or Barcelona or Tokyo. It shouldn't be possible, but there they are, shimmering and glowing in infrared wavelengths that only telescopes like Webb can see. Third thing, and this one really gets into strange territory, there's a tiny object out beyond Neptune's main orbit, something we call 2020 VN40. It's probably not very big, maybe a small asteroid or a chunk of rock that got kicked out from somewhere else in the solar system. Nothing particularly special about it, or at least nothing special until you look at its orbit. This object completes exactly 10 orbits around the Sun for every single orbit that Neptune completes. Not 9.9, not 10.1, exactly 10 every single time. That kind of mathematical perfection doesn't happen by accident. That's the result of some incredibly precise gravitational choreography, and nobody really understands how it happened or why it's so perfectly synchronized. And fourth, the thing that really ties all of this into a knot that we can't untangle yet. Neptune's largest moon, a world called Triton, shouldn't even be there. It orbits backwards relative to how Neptune rotates. It comes in at an angle of 130 degrees to everything else in the system. And unlike most moons, which are just dead, cold, barren rocks, Triton is doing something that almost no other moon in our solar system is doing. It's actively erupting. Volcanoes made of ice and water and methane are firing material up into a thin atmosphere, and the surface is covered with organic compounds, the basic chemical building blocks of life. Scientists have been debating for years whether there could actually be life hiding beneath Triton's frozen crust, in an underground ocean warmed by the moon's own internal heat. Now they're wondering if maybe that question is more urgent than they thought. So we have 4 mysteries: a planet that's freezing when it should be warming up, auroras in all the wrong places, a tiny object in a perfect cosmic dance, and a moon that seems far too alive for somewhere so far from the sun. How do these 4 things connect? What do they tell us about Neptune? And more importantly, what do they tell us about how little we actually understand about the universe? Welcome. I'm going to spend the next 2 hours walking you through every single piece of this puzzle. We're going to go back to 1846, and follow the incredible story of how we even found Neptune in the first place. It's a story that involves mathematics, prediction, and one of the most stunning moments in the history of science. Then we're going to move forward to 1989, when Voyager 2 flew past this distant world and sent back images that shocked the astronomical community. We'll talk about the storms that form and disappear, vanishing completely and then reappearing years later, as if nothing happened. We'll dig into what we know about the planet's interior, where the pressure is so extreme that methane might be breaking apart and reforming as solid diamonds, creating a rain of diamond hail that would make the wealthiest people on Earth weep with envy. We'll explore the entire moon system, 13 other worlds orbiting in the darkness, including moons so small we didn't even know they existed until recently. We'll talk about how Neptune's gravity reaches out across the solar system and influences objects billions of kilometers away. And we'll finish by looking at what the future might hold, because there are people right now working on plans to send a new spacecraft to Neptune, something that hasn't happened in more than 50 years. If that mission actually launches, we might finally get some real answers to these questions that are driving scientists absolutely crazy right now. But first, let's go back in time, because the story of Neptune doesn't begin with the James Webb Space Telescope. It doesn't even begin with Voyager 2 or any of the modern astronomy tools we have available today. It begins with one man, a mathematician in France, who looked at numbers and realized something impossible. It's 1846, Paris. There's a scientist named Urbain Jean-Joseph Le Verrier. He's sitting in his study, looking at astronomical data from observations of the planet Uranus. And he notices something off. Uranus isn't moving quite where Newton's laws of motion predict it should be moving. The gravitational pull from the Sun and Jupiter should account for where Uranus is, but it doesn't. Uranus is slightly off, slightly perturbed, like something is pulling on it from the outside. Le Verrier thinks about this. He runs the mathematics again and again, and he comes to a conclusion that seems absolutely insane. The only way Uranus could be where it is, the only way the numbers could work out, is if there's another planet, a planet we haven't discovered yet, a planet that exists beyond Uranus and is exerting a gravitational pull. So Le Verrier does the calculations. He figures out where this theoretical planet would have to be. He actually predicts the exact location in the sky where this undiscovered world should be. And then he tells his friend, Johann Galle, a telescope operator at an observatory in Germany. He says, "Look here, at this specific location. There's going to be a planet there." Galle points his telescope at the location Le Verrier specified. He looks through the eyepiece, and he finds it. He actually finds it. He discovers Neptune in one single hour. It was almost exactly where Le Verrier predicted it would be. Think about that for a moment. We didn't find Neptune by accident. We didn't stumble across it while looking at something else. We found it because someone did math and said, this is where it has to be. And then we looked there and it was exactly where they said it would be. That's one of the most stunning intellectual achievements in the history of astronomy. It's one of the most stunning intellectual achievements in the history of science, period. It proved that we could understand the universe through mathematics, that we could predict the existence of worlds we'd never seen, that the universe followed rules, and those rules could be written down and understood by the human mind. But here's the thing about Neptune. Ever since we found it, it's been a puzzle, a mystery wrapped in ice and darkness. Because Neptune is not like the other planets in our solar system. It's not like Earth, where you can build a telescope, point it up, and see it clearly on a reasonably dark night. It's not like Jupiter or Saturn, which are bright enough that you can pick them out without too much difficulty. Neptune is the 8th planet from the Sun. It orbits about 4.5 billion kilometers away from Earth. That's 30 times farther from the Sun than we are. To give you some perspective on what that means, the Sun looks like a tiny pinpoint in Neptune's sky. Imagine holding a pinhead at arm's length. That's how big the Sun appears from Neptune's surface. And the light takes hours and hours to get there. The darkness is complete. The cold is unimaginable. Because it's so far away and so dim, we can't study it very easily with ground-based telescopes. The light coming from Neptune is just too faint. So for most of human history, we basically didn't know anything about it. We knew it was there. We knew where it was in the sky. We knew its basic orbital parameters. But we didn't actually know what it looked like or what it was like or what was happening on its surface or in its atmosphere. That all changed in 1989, when Voyager 2, the only spacecraft that has ever actually visited Neptune, flew past it. Voyager 2 had been traveling for nearly 3 years to get there, moving at a speed of 54,000 kilometers per hour. When it finally approached Neptune, it sent back the first close-up images we'd ever seen of this distant world. What Voyager 2 revealed was a planet covered in clouds and storms. There were jet streams in the atmosphere moving at incredible speeds, up to 2,400 kilometers per hour. That's nearly supersonic. There was a giant dark spot, similar to the Great Red Spot on Jupiter, moving through the atmosphere and generating winds of extraordinary intensity. There were smaller storms, smaller disturbances, all kinds of weather systems going on. The planet was far more active and dynamic than anyone had expected. And then the spacecraft sent back images showing that Neptune has a ring system, not as prominent or as spectacular as Saturn's rings, but rings nonetheless. Those rings were a surprise. Scientists had suspected they might exist, but Voyager 2 confirmed it. And the probe discovered several new moons orbiting the planet, additions to our understanding of the Neptune system. After Voyager 2 flew by, Neptune went back to being largely ignored by the astronomical community. It was just too far away, too difficult to study, too inaccessible. We didn't have another spacecraft going there, and ground-based telescopes could barely see it. So we just kind of left Neptune alone in the darkness. Every now and then, the Hubble Space Telescope would point at it and send back some updated images. Hubble has been incredibly valuable for tracking changes in Neptune's atmosphere over the decades. But mostly Neptune was this distant, mysterious world that we didn't really have the capability to observe very closely. And then, a few weeks ago, James Webb turned its eye in that direction. And suddenly, we're seeing things we've never seen before. We're seeing auroras that shouldn't exist. We're seeing temperature changes that don't make physical sense. We're seeing evidence of complex interactions happening at Neptune that challenge everything we thought we understood about how ice giant planets work. And that's why we're here. That's why I'm talking to you about this right now, because Neptune just became one of the most important puzzles in astronomy, and nobody has the answers yet. The scientists are confused. The data doesn't fit the models, and the more we learn from Webb's observations, the more questions we have. So let's start figuring this out together. Let's become amateur detective astronomers and see if we can piece together what's actually happening at the edge of our solar system. Because I promise you, by the end of this, you're going to understand why Neptune matters. You're going to understand why a tiny, distant, barely visible ice giant is keeping some of the smartest people in the world awake at night. And you're going to understand why the answers to Neptune's mysteries might actually change how we think about planets throughout the entire universe. Now let's talk about what happened between 1989 and now, between that Voyager 2 flyby and the James Webb observations. Because when scientists compare those two sets of data, they run into their first major problem, their first big mystery. Neptune has gotten colder, significantly colder, the kind of colder that doesn't make sense when you think about how planetary physics should work. When Voyager 2 measured Neptune's upper atmosphere in 1989, it recorded temperatures hovering around -201 degrees Celsius. That's -330 degrees Fahrenheit. It's so cold that every chemical compound you can think of would freeze solid. Your breath would freeze before it left your mouth. Water would turn into rock. Carbon dioxide would become a solid block. It's so cold that human civilization simply wouldn't survive for more than minutes in those conditions. But here's the thing, as cold as it is, scientists thought that was just how Neptune's upper atmosphere had to be. That was just the temperature you'd expect for a planet so far from the sun, receiving so little of the sun's warmth. They plugged those numbers into their models, they ran the calculations, and they figured, okay, that's Neptune, that's what we should expect. Then, starting in the early 2000s, when ground-based telescopes began to get better at observing Neptune in infrared wavelengths, astronomers started collecting more data. Between 2003 and 2018, researchers gathered thermal infrared images from all over the place. They used the Very Large Telescope in Chile. They used the Gemini South Telescope, also in Chile. They used the Subaru Telescope in Hawaii. They used the Keck Telescope. They used the Gemini North Telescope. They even pulled data from NASA's Spitzer Space Telescope. When they pooled all that data together, when they analyzed nearly 100 separate thermal images of Neptune taken over more than a decade and a half, they found something that made them pause and look at their calculations twice. Neptune had gotten colder, but not by a small margin, not by a degree or two. The planet's globally average temperatures in its stratosphere had dropped by 8 degrees Celsius. That's 14 degrees Fahrenheit, in a decade and a half. Let me put that in perspective. If the exact same thing happened to Earth over the same time period, we would be in an ice age. We would be experiencing catastrophic climate change. We'd be talking about civilization-ending temperatures, mass extinction events, the collapse of everything we know, and that would only be a drop of 14 degrees. Neptune dropped by 14 degrees in a decade and a half, and nobody could explain why. The immediate thought is, okay, maybe the sun's activity changes. Maybe solar cycles affect Neptune's atmosphere. Scientists know that the sun goes through cycles. There's an 11-year solar cycle where the sun's magnetic activity waxes and wanes. Maybe that affects Neptune too. Maybe when the sun's activity is lower, Neptune cools down. So they looked into that. They studied the solar cycle data, and it didn't line up. The sun's activity cycle didn't match Neptune's temperature drop. So that wasn't it. Maybe it's seasonal. Neptune has seasons, just like Earth does. Neptune is tilted on its axis, about 28 degrees, similar to Earth's 23-degree tilt. This means the planet experiences seasonal shifts in which hemisphere gets more sunlight. Neptune takes 165 years to orbit the Sun, so each season lasts about 40 years. Right now, Neptune's southern hemisphere is in spring. It's experiencing more sunlight than the northern hemisphere. But even so, the amount of additional sunlight we're talking about is minuscule. The Sun's so far away and so dim that a seasonal shift in solar exposure wouldn't account for a 14-degree drop in global temperatures. So that wasn't it either. Maybe it's something in the atmosphere itself, maybe chemical reactions in Neptune's atmosphere, maybe shifts in how methane and other compounds absorb and re-radiate heat, maybe something changed in the composition or structure of Neptune's cloud layers. But when scientists looked into that, they couldn't find any clear evidence of dramatic chemical changes that would account for the cooling. So that wasn't it. Then, in 2023, James Webb took a measurement that completely threw everyone off. Webb looked at Neptune's upper atmosphere and measured the temperature once more, and the new measurement showed that temperatures in 2023 were just over half of what they were in 1989. We're not talking about 14 degrees anymore. We're talking about a temperature that had essentially been cut in half over the course of 34 years. That's not a gradual cooling. That's not a seasonal fluctuation. That's a dramatic, unprecedented, completely unexplained transformation of Neptune's upper atmosphere. Glenn Orton, a research scientist at NASA's Jet Propulsion Laboratory, actually said that they were, quote, astonished by this finding. The data shows that Neptune's upper atmosphere has cooled by several hundreds of degrees. Lee Fletcher, an astronomer at the University of Leicester who led the Webb observations, put it in even starker terms. He said that the dramatic cooling suggests that this region of the atmosphere can change greatly even though the planet sits over 30 times farther from the Sun compared to Earth. In other words, Neptune's atmosphere is changing on a scale that violates our understanding of how planetary atmospheres should work when they're this far from the energy source that's driving all the weather systems. Now here's the really important part, because this cooling is directly connected to the second mystery we mentioned. It's directly connected to the auroras. When Voyager 2 flew by in 1989, instruments detected that Neptune should have auroras. The theory said, okay, this planet has a magnetic field. Solar wind interacts with that magnetic field. You should get auroral emissions just like you see on Jupiter and Saturn and Earth. But for decades, no one could actually see Neptune's auroras. Telescopes from Earth couldn't detect them. Hubble couldn't detect them. Webb had to wait until 2025 to finally capture clear images of them. And when Webb finally did see them, when the first infrared images came back showing those ghostly green auroras wrapped around the planet's mid-latitudes, one of the scientists involved in the observations, someone named Mellin, was so surprised that he immediately said, "I was astonished." The reason those auroras had been so hard to see was the temperature. Astronomer had predicted that if Neptune's upper atmosphere was as cold as Voyager 2 said it was, the auroras should be very faint, barely detectable, almost impossible to see, but they were still expecting to see them eventually. Then, as Webb started measuring, scientists realized that Neptune's upper atmosphere had cooled so dramatically that the auroras would be even fainter than predicted. So faint that ground-based telescopes and even older space telescopes couldn't detect them. That's why it took the most advanced infrared observatory humanity has ever built to finally see them. This is where the mystery gets really interesting, because now we have a feedback loop. Neptune cooled, which made the auroras fainter, which made them harder to detect, which meant we couldn't study them for decades, which meant we missed crucial data about what was happening in Neptune's atmosphere. And that brings us to the storms. Because if Neptune's atmosphere is changing this dramatically, if temperatures are dropping this precipitously, then the storm systems have to be changing too. When Voyager 2 flew past Neptune in August 1989, it saw this massive storm. The engineers gave it a name. They called it the Great Dark Spot, and it was exactly what it sounds like. A dark blemish on Neptune's atmosphere, a vortex, a storm system, something like the Great Red Spot on Jupiter, but moving and changing faster. The Great Dark Spot on Neptune was estimated to be about the size of Earth. Maybe not quite as big, but close. It was massive, and the winds around it were moving at about 2,400 kilometers per hour. That's almost twice as fast as the fastest winds we see on Jupiter. That's faster than the fastest wind speeds we see anywhere in the entire solar system, except for Neptune itself. The storm was violent, chaotic, and absolutely fascinating to the scientists studying it. The natural assumption was that this great dark spot would stick around for a while. These major storm systems can persist for years. Scientists thought they'd be able to keep observing it, watching how it evolved, tracking its movements. They got excited. This was going to be a long-term study. This was going to provide valuable data about Neptune's atmosphere and how it works. Then, in 1999, Hubble pointed at Neptune for the first time and looked where the great dark spot had been. and it wasn't there anymore. It had completely vanished, just gone. No trace of it left. Astronomers were confused. They double-checked their observations. They looked at the images multiple times. It was definitely gone. The storm that had been the size of Earth had simply disappeared. That's when things started getting really weird, because it's not like the Great Dark Spot gradually faded away. It's not like it slowly weakened over 10 years and eventually dissipated. It was there in 1989. It was gone by 1999. That's a decade, and in that decade, a storm system the size of Earth just ceased to exist. Scientists tried to figure out why. They ran models. They studied the atmospheric dynamics. They looked at how smaller storms dissipate, and they couldn't come up with a completely satisfying explanation for why such a massive storm would vanish so completely and so quickly. But then it got even stranger, because if there's one thing we've learned about Neptune, it's that the planet likes to keep surprising us. In 2015, astronomers spotted a new dark spot appearing in Neptune's southern hemisphere. They called it the Southern Dark Spot, or SDS for short, and they started tracking it carefully. They watched as it moved across the planet. They knew from the Great Dark Spot's experience that these storms don't last forever, but they were hoping this one would stick around long enough to get some good observations. Then, in 2018, another dark spot appeared, this time in Neptune's northern hemisphere. This one was smaller than the SDS from 2015, and it was one of the first dark spots that Hubble was able to track from the moment it was born. Astronomers got really excited about this because they'd never seen the formation process of one of these storms before. They'd always caught them after they'd already formed, but this one they could watch from the very beginning, so they tracked it. They watched how it moved. They followed its path as it drifted southward toward Neptune's equator. In August 2020, something unexpected happened. The dark spot that had been moving steadily southward suddenly stopped. It made a sharp U-turn. It started moving northward again, going back in the direction it came from. This reversed motion was shocking to the astronomers. The computer simulations and the theoretical models they'd built suggested that storms moving toward the equator eventually dissipate when they get there because the Coriolis effect weakens. But this storm didn't dissipate. It turned around and came back north. At almost the same time that the storm reversed direction, a smaller dark spot appeared near the larger one. Astronomers called this smaller storm Dark Spot Junior, and they thought, based on the timing and the proximity, that Dark Spot Junior might have formed when the larger storm began to break apart. Maybe the stress that caused the larger storm to reverse direction also caused it to fragment. Maybe Dark Spot Junior was a piece that broke off. It was an entirely new process being observed, something that theoretical models had predicted could happen but had never actually been seen before. By 2021, Dark Spot Junior had disappeared. It was gone. Then, the larger dark spot eventually faded away too. So we went from having multiple storm systems visible on Neptune to having none. All the dark spots were gone. The planet's face was clear. Michael Wong, an astronomer from UC Berkeley, commented that this process, the disruption process, had never been observed before. They'd seen dark spots fade away over the years. They'd seen them come and go, but they'd never actually seen the disruption process in action, the moment when a storm breaks apart. Here's what makes this all connect back to the temperature mystery. If Neptune's atmosphere is cooling so dramatically, if temperatures are dropping by hundreds of degrees, then the dynamics of how storms form and how they behave have to be changing too. The energy available to power these storm systems is connected to the temperature. If the atmosphere is getting colder, the energy landscape is shifting. The way heat flows, the way pressure gradients develop, the way winds move, all of it has to be affected. So the Great Dark Spot disappearing, so the storms appearing and vanishing unpredictably, so the reversals in direction, all of it might be connected to this mysterious, unexplained, dramatic cooling that's happening. But here's the thing. We don't have enough data to confirm that. We don't have continuous observations from 1989 to now. We have snapshots. We have Voyager 2 in 1989. Then there's basically nothing until Hubble starts looking at the planet in the late 1990s. Then there's Hubble observations here and there through the 2000s and 2010s. Then WEBB shows up in 2023 and 2024 and 2025 and finally gives us really detailed, high-resolution observations. So we have these data points scattered across decades, but we don't have a complete picture. We don't have the continuous movie that would let us understand exactly what's been happening. We're trying to reconstruct a story based on photographs taken decades apart. It's like if you wanted to understand how a human grows from a baby to an adult, but you only had 3 photographs, one from when they were born, one from when they were 20, one from when they were 60. You could make some observations based on those 3 photos, but you'd miss so much. You'd miss all the intermediate changes. You'd miss the growth spurts and the transformations. You'd have gaps in your understanding. That's basically what we have with Neptune. We have these isolated moments in time where we can see what the planet looks like, but we don't have the continuous story in between. So the question becomes, where does this cooling come from? Why is Neptune's atmosphere getting so much colder? Scientists have some theories, but none of them are completely satisfying yet. One possibility is that there's some kind of internal heat source that's becoming less active. Neptune does radiate more heat than it receives from the sun. There's internal energy, probably from the planet's formation, radiating outward. Maybe that heat source is fluctuating. Maybe it goes through cycles. Maybe right now, we're in a cycle where the internal heat output is lower than it's been in the past. That would explain why the upper atmosphere is cooling. But if that were true, we should see the entire planet getting cooler, not just the upper atmosphere. And we don't see that pattern, so that's probably not the whole story. Another possibility is that there's something changing in the atmospheric chemistry. Maybe the concentration of methane or other gases is shifting. Maybe the way light interacts with the atmosphere is changing. Maybe the clouds are forming in different patterns than they used to. Any of those changes could affect how efficiently the atmosphere radiates heat away into space. But when scientists look for evidence of those kinds of chemical changes, they don't find much. So that's probably not it either. At least not the whole explanation. The most likely answer, the one that most astronomers are leaning toward, is that we simply don't understand how Neptune's atmosphere works well enough yet. The planet is doing something that violates our current models and our current predictions. It's telling us that there are processes happening in ice giant atmospheres that we haven't accounted for in our theoretical frameworks. And that's actually incredibly exciting from a scientific perspective. Because when reality doesn't match your models, that means there's something new to discover. That means there's a piece of the puzzle that's still missing. And finding that piece, figuring out what we're not accounting for, that's where real progress in science comes from. So we have these two massive mysteries tied together. A planet that's getting colder for reasons we can't fully explain, and storms that are appearing and disappearing and behaving unpredictably. And these two mysteries are connected to a third mystery, the auroras that are showing up in the wrong place. We already talked about how the auroras were so faint that they weren't detected until WEBB came along. But there's more to the story than just that. The place where Neptune's auroras are showing up is completely different from what we'd expect based on how auroras work on every other planet in the solar system. On Earth, auroras happen at the poles. On Jupiter, they happen at the poles. On Saturn, they happen at the poles. The pattern is simple. Auroras are caused by charged particles from the solar wind interacting with a planet's magnetic field. The magnetic field funnels those particles down toward the magnetic poles. The particles crash into the upper atmosphere and create light. It's a beautiful process. And it's predictable. We understand how it works. On Neptune, everything is different. Neptune's auroras aren't at the poles, they're at the mid-latitudes. They're happening at what you might call the planet's equator, or at least around the middle of the planet, rather than at the top or bottom. It's as if Neptune's auroras are showing up in the wrong place entirely. And the reason for this goes back to something that Voyager 2 discovered. Neptune's magnetic field is weirdly tilted. Normally, a planet's magnetic field aligns roughly with its rotational axis. On Earth, our magnetic north pole is pretty close to our geographic North Pole. They're offset by a few degrees, but they're basically aligned. The same is true for most other planets. Jupiter's magnetic field is roughly aligned with its rotation. Saturn's is too, but Neptune is different. Neptune's magnetic field is tilted at 47 degrees from its rotational axis. That's a huge offset. It's like if your magnetic North Pole was pointing toward Mexico when your geographic North Pole is pointing toward the Arctic. The magnetic field is so tilted that the magnetic poles end up in completely different locations than you'd expect. This strange tilting of Neptune's magnetic field is what causes the auroras to show up at the mid-latitudes instead of the poles. The magnetic field converges into the planet's atmosphere at the mid-latitudes, so that's where the charged particles from the solar wind end up, and that's where the auroras happen. It's a totally bizarre configuration, and it makes Neptune's magnetosphere one of the most interesting and least understood magnetic environments in the entire solar system. Now here's where it gets even more interesting. No one fully understands why Neptune's magnetic field is tilted like this in the first place. Is it because of the planet's internal structure? Is it because of how the planet formed? Is it something that changes over time? Scientists have theories, but no one has definitive answers. Some models suggest that the magnetic field might be generated not in the planet's core, but in a conducting liquid layer within the mantle. If that layer is thick and distributed in a particular way, it could create an offset like we see. Other models suggest that maybe the mantle is so conducting that it deflects the magnetic field emanating from the core, causing this weird tilt. But these are still just theories. What WEBB is going to help us do over the coming years is study Neptune's magnetosphere over a full solar cycle. That's an 11-year period. By watching how Neptune's auroras respond to changes in solar activity over those 11 years, scientists hope to gain insights into how the magnetic field actually works and why it's configured the way it is. That data could answer some fundamental questions about Neptune. It could tell us about the planet's internal structure, about how its magnetic field is generated, about the fundamental fundamental processes that drive the planet's magnetic behavior. Right now, I want to shift our attention to something even more bizarre than cooling temperatures and disappearing storms. I want to talk about the thing that first caught our attention when we looked at Neptune. I want to talk about Triton, because Triton isn't just a moon, it's a kidnapped planet. It's a world that doesn't belong there, and the fact that it's where it is changes everything about how we understand the Neptune system. Let me explain what makes Triton so strange. First, the basics. Triton is Neptune's largest moon. It was discovered in 1846, just days after Neptune itself was discovered. It's a world that's roughly the size of our own moon, though it's actually a bit smaller. It orbits Neptune once every 5.87 days. But here's where it gets weird. Triton orbits Neptune in the wrong direction. It moves retrograde. It orbits backwards, in the opposite direction from how Neptune rotates. Now, if you think about it, that shouldn't be possible for a large moon. When planets form, they form out of a disk of material rotating around a star. Everything in that disk rotates in the same direction. Planets inherit that rotation. Moons that form naturally from the leftover material in a planetary system also inherit that rotation. They should all spin the same way. You don't get large moons orbiting backwards unless something very unusual happened. You don't get a moon in a retrograde orbit unless it wasn't born in that system, unless it was captured from elsewhere. And that's exactly what scientists think happened with Triton. Triton is a captured object. It wasn't born as a moon of Neptune. It formed somewhere else, in the Kuiper Belt, as an independent body. It was a full-fledged dwarf planet, probably similar in nature to Pluto or Eris. And then, billions of years ago, it drifted too close to Neptune, got caught in the planet's gravitational pull, and was forced into an orbit around Neptune. Now here's the really fascinating part. When Triton got captured, it didn't immediately settle into a nice circular orbit. Instead, it went into a highly elliptical, very elongated orbit. Imagine a huge oval path around Neptune, where sometimes Triton gets really close to the planet, and sometimes it gets really far away. When you have an orbit like that, you get massive tidal forces. The gravitational pull from Neptune on the side of Triton facing the planet becomes much stronger than the pull on the far side. This creates enormous tidal stress. It's like Neptune is trying to stretch Triton, pulling it from one side while the other side resists. All that stress, all that friction from the tidal forces generates heat inside Triton. Lots of heat. It's actually enough heat to melt ice. Over millions of years, as Triton orbited in that highly elliptical path, the tidal friction gradually wore away at the orbit, making it less and less elliptical. Eventually, it became the nearly circular orbit we see today. But during all that time, all those millions of years, Triton was being heated internally by the tidal forces. And that internal heat, scientists believe, is what created something extraordinary beneath Triton's icy surface. A subsurface ocean, liquid water, probably a few hundred kilometers beneath the ice shell, warmed from below by Triton's rocky radiogenic core, not actively heated anymore the way it was when Triton's orbit was more eccentric, but still warm enough, still active enough, that life could theoretically survive there. But wait, it gets even better, because Triton isn't just sitting there dead and quiet anymore. Triton is actively doing something. Triton is erupting. When Voyager 2 flew past Triton in 1989, it captured images of something absolutely astounding. Geysers, cryovolcanoes, plumes of material shooting up 8 kilometers into the air. Not lava, because it's too cold for lava on Triton. Instead, these geysers are spouting nitrogen gas, methane gas, water, and other ices from beneath the surface. The material freezes almost instantly as it hits the cold upper atmosphere, and it falls back down as a kind of frost or snow. But it's still eruption. It's still volcanic activity. It's just volcanic activity with ice and frozen gas instead of molten rock. Here's what really drives this activity. Here's the mechanism that keeps Triton alive. Under the icy crust, there's liquid water. That water is in contact with the rocky metallic core. The core contains radioactive elements, uranium, thorium, potassium, various isotopes that undergo radioactive decay. When those elements decay, they release energy. That energy heats the water. The heated water warms the overlying ice. In some places, the temperature gets high enough to melt the ice from below. You get pockets of liquid water that build up pressure, and when the pressure gets high enough, it finds a path to the surface. It cracks through the ice, and it erupts. The really mind-blowing part is that the surface of Triton is incredibly young. We know this because of the lack of impact craters. In the solar system, older surfaces get bombarded by asteroids and smaller bodies over billions of years. They accumulate impact craters. Younger surfaces don't have as many craters because there hasn't been as much time for impacts to accumulate. When scientists look at Triton, they see very few impact craters. That means Triton's surface is young. That means it's been resurfaced relatively recently. That resurfacing has been happening because of cryovolcanism. The eruptions bring fresh ice and frozen material to the surface, covering up the old terrain, creating a young face. And that leads to an incredible possibility. A possibility that NASA scientists have been quietly discussing for years. Beneath Triton's ice, in that subsurface ocean, there might be life, or at least, there might be conditions suitable for life. We know from studies of Earth's oceans that life can exist in extreme environments, around hydrothermal vents, in total darkness, in conditions that seem impossibly hostile. But life finds a way. Life colonizes those environments. Scientists call these environments chemosynthetic ecosystems. They don't require sunlight. They don't require the sun's energy at all. They run on chemical energy, on the energy from hydrothermal reactions between rock and water. Triton has exactly those conditions. It has a rocky core in contact with liquid water. It has hydrothermal activity. It has all the ingredients you'd need for chemosynthetic life. So scientists have started asking whether Triton might harbor life, whether right now, beneath the frozen surface, there might be organisms living in that subsurface ocean, powered by chemical energy from the planet's interior. That question gets even more interesting when you look at Triton's surface composition. Because Triton's surface isn't just water ice, it also has methane, nitrogen, carbon dioxide, and something else, something really important. Organic compounds, tholins. These are molecules that form when organic material gets exposed to ultraviolet light from the sun. On Triton, there's probably not much UV light hitting the surface because the sun is so dim and so far away. But there might be cosmic rays. There might be radiation from other sources. And whatever the source of radiation, it seems to have created tholins on Triton's surface. Now, tholins are significant because they're organic, they're carbon-based, they're the kind of compounds that life is made of. They're not life themselves, but they're the basic building blocks of life. They're like finding flour, sugar, and eggs in a kitchen. They're not a cake yet, but they're the ingredients you need to make a cake. On Triton, these organic compounds are being created, probably as a result of radiation interacting with simpler molecules on the surface. And some of that organic material might be making its way to the subsurface ocean through cryovolcanic eruptions, getting brought to the surface from below and exposed to radiation. So you have a subsurface ocean with energy available from hydrothermal processes. You have organic compounds being created at the surface. You have a mechanism for bringing those compounds into contact with the ocean. You have everything you need for life. You have a world that is, scientifically speaking, potentially habitable. And this world is orbiting Neptune. Right now, it's been there for billions of years. It might have life. We don't know. This brings us to something that's been puzzling astronomers for a long time. How is Triton different from other large moons in the solar system? Why does Triton seem so much more alive than other icy moons like Europa or Enceladus? The answer appears to be related to its capture. When Triton was captured by Neptune's gravity, it went through a period of intense tidal heating. That period lasted for millions of years. During that time, Triton was extraordinarily active. It was melting, deforming, heating internally. And that process, that violent capture and incorporation into Neptune's system, that seems to have been what created the conditions for life beneath Triton's surface. Think about what that means. Most moons formed peacefully as part of their planetary system from material that was already there. They've been cold and relatively dormant since their formation. But Triton had a violent birth as far as its current orbit is concerned. It was kidnapped. It was thrown around by gravitational forces. It was heated and stressed and forced to circularize its orbit. And that violence, that trauma, might be what gave Triton its potential for life. Recent research has added another layer to this story. Scientists have been studying what happens when an object like Triton is captured, and they've found something unexpected. They thought that the tidal heating would happen only briefly during the capture process, and the early phase of orbit circularization. They thought Triton would cool down quickly. But when they ran more sophisticated models, accounting for various factors like ice shell melting and internal feedbacks, they found that the tidal heating could persist for billions of years, for 1 to 4 billion years, according to recent calculations. Triton's ice shell could have been very thin, just 1 to 10 kilometers thick, for a very long time. And that thin ice shell would have meant that tidal stresses could fracture it completely, potentially allowing material to exchange between the subsurface ocean and the surface. That exchange would bring organic compounds down and possibly bring mineral-rich water up, creating an environment even more suitable for life. And then, after all that time, as the tidal dissipation finally waned, as Neptune's gravitational pull stopped heating Triton's interior so intensely, something else could have happened. The ice shell could have thickened. The subsurface ocean could have pressurized. That pressurization could have caused the ice shell to fracture one more time, allowing one final massive eruption of cryovolcanic activity that resurfaced large portions of Triton and gave it the young appearance we observe today. This is all very recent research. This was published in 2024. It's only been a few months since the astronomical community has been grappling with these ideas. But what it suggests is that Triton, this little captured world at the edge of our solar system, has a much longer story of potential habitability than we previously understood. It's not just a world that might have life now. It might have had conditions suitable for life for billions of years. It might have been a haven for life for nearly the entire history of the solar system. Now here's where this connects back to everything else we've been talking about. Here's where Neptune's mysteries start to form a coherent picture. We have a planet whose atmosphere is cooling for reasons we don't understand. We have storms appearing and disappearing unpredictably. We have auroras in the wrong place. And we have a moon system that seems designed to house life. What does it all mean? How do these pieces fit together? The answer might be that Neptune itself is more dynamic, more active, more alive than we previously realized. Neptune isn't just a static, unchanging ice giant slowly rotating in the darkness billions of kilometers away. Neptune is a world with internal processes that change its atmosphere, with magnetic fields that create auroras, with a gravitational field powerful enough to capture objects from the Kuiper belt and hold them in orbit, with moons that might harbor life beneath their ice. Neptune is a system in motion. It's a system with stories to tell, and we're only just beginning to listen to those stories. But there's one more mystery we need to unpack, one more piece of the puzzle that's been sitting out there in the darkness, in an orbit that shouldn't exist, following a pattern that defies our understanding. We need to talk about 2020 VN40. We need to talk about the object in the perfect cosmic dance. Before we get to that, though, I want to make sure you understand just how isolated Triton is, how far it orbits from Neptune, and how far Neptune itself is from everything else. Neptune orbits about 4.5 billion kilometers from the Sun. That's 30 times farther than Earth. The nearest star to our Sun, Proxima Centauri, is about 40 trillion kilometers away. Just to give you a scale, if you were standing on Neptune looking back at the Sun would be a pinpoint, barely brighter than the brightest stars in the sky. You could easily mistake it for an ordinary star if you didn't know better, and Proxima Centauri would be so impossibly distant that there's no meaningful way to conceptualize the separation. Triton orbits at a distance of about 355,000 kilometers from Neptune. That's a bit less than the distance from the Earth to the Moon. So from Triton's perspective, Neptune fills a portion of the sky, not dominating it, but definitely being the most impressive object. And as for the Sun would be completely washed out by Neptune's reflected sunlight. You couldn't see the Sun from Triton's surface in daylight. You might be able to see it from Triton's night side if you knew exactly where to look, but it wouldn't be impressive. This is the scale we're working with. Triton is alone with Neptune in the darkness, orbiting in a retrograde path, harboring a potential subsurface ocean, geysers erupting into the thin atmosphere, organic compounds coating the surface. And this is just one moon in Neptune's system. There are 13 other moons. Most of them are tiny, barely visible, capturing barely any attention from the broader astronomical community. Some of them were only discovered recently because better telescopes finally made them visible. One of them, Hippocamp, was discovered as recently as 2013 by the Hubble Space Telescope. And then there's 2020 VN40, a tiny object, probably no more than a few kilometers across, orbiting somewhere beyond Neptune's regular moon system, an object that nobody knew existed until relatively recently. An object that shouldn't be there, that shouldn't be doing what it's doing, that shouldn't be following the orbital pattern that it's following. An object that's locked in a perfect mathematical relationship with Neptune itself, and nobody can fully explain why. Let's talk about something that sits at the absolute edge of the observable solar system. Something so far away that light takes hours to get there. Something so small that we just discovered it recently. And something so bizarre in its behavior that it's become one of the hottest topics in planetary science right now. 2020 VN40. That's the official name. It's not as catchy as something like Pluto or Eris, but the numerical designation hides something extraordinary about what this object is doing. First, the basics about what we're looking at. 2020 VN40 is a trans-Neptunian object. That means it orbits the Sun beyond Neptune's orbit. It's probably only a few kilometers across, so it's quite small. It's definitely smaller than our Moon. It orbits the Sun in a highly eccentric and highly inclined orbit, which means its orbit is stretched out and tilted dramatically compared to the flat plane in which most planets and asteroids orbit. It's out at a distance of about 140 astronomical units from the Sun. To put that in perspective, Neptune orbits at about 30 AU, Earth orbits at 1 AU. So this object is about 140 times farther from the Sun than we are. The discovery of 2020 VN40 is itself interesting. It was found by the LIDO survey, which stands for Large Inclination Distant Objects Survey. This survey was specifically designed to look for trans-Neptunian objects that have high inclination orbits, meaning orbits that are steeply tilted relative to the ecliptic plane. Most surveys concentrate on looking near the ecliptic, where most objects are concentrated. But LIDO looked above and below that plane, and over the course of multiple years of observation, tracking the object from 2020 all the way through 2022, astronomers were able to determine 2020 VN40's orbital parameters with enough precision to make a surprising discovery. This object is locked in a perfect 10-to-1 orbital resonance with Neptune. Let me explain what that means, because it's genuinely one of the most fascinating concepts in orbital mechanics. Imagine two dancers. They're dancing to the same music, but they're dancing at different speeds. One dancer completes one full dance move, while the other completes 10 dance moves, but they do it in such a way that they always meet at the same point in space at the same time. They're synchronized, they're resonant, their movements are locked together by the music and by their awareness of each other's position. That's what's happening with Neptune and 2020 VN40. Neptune takes about 165 years to orbit the Sun. 2020 VN40 takes about 1,655 years to orbit the Sun. That's about 10 times longer. So while Neptune completes one full orbit around the Sun, 2020 VN40 completes exactly 1/10 of an orbit. It's a 10-to-1 ratio. 10-to-1, not 9.8-to-1, not 10.2-to-1, exactly 10-to-1. And that perfect mathematical relationship isn't a coincidence. It's the result of gravitational interactions that have locked these two objects into orbital synchrony. Here's how it works. When two objects orbit the Sun with periods that are in a simple integer ratio, they experience periodic gravitational pulls from each other. If those pulls happen at just the right times in each object's orbit, they can reinforce each other. The gravitational tug from Neptune on 2020 VN40 happens at just the moment when it's most useful for keeping 2020 VN40 in its resonant orbit. The effect is cumulative. Over time, over millions of years, the gravitational interactions lock the two objects into an exact resonance. This isn't unique to Neptune and 2020 VN40. There are other examples of orbital resonances throughout the solar system. Pluto, for instance, is in a 2-to-3 resonance with Neptune. For every 2 orbits Pluto makes, Neptune makes 3 orbits. That's why Pluto never gets pulled out of the Kuiper belt. Neptune's gravity keeps it in a stable resonance. There are other objects in other resonances. Jupiter's Trojan asteroids, those groups of asteroids that huddle in the gravitational equilibrium, point 60 degrees ahead and behind Jupiter. They're in a 1-to-1 resonance with Jupiter. They're at the same distance from the Sun as Jupiter, so they complete 1 orbit for every 1 orbit of Jupiter. They're permanently stuck in Jupiter's orbital path. But 2020 VN40 is different. It's in the 10-to-1 resonance, and that makes it incredibly rare. It's the first object confirmed to be in this particular resonance with Neptune. Scientists have theorized that objects in high integer resonances like 10-to-1 or 7-to-1 or 5-to-1 should exist, but actually finding them is difficult. Most known resonances are in lower integer ratios, 2-to-3, 1-to-2, things like that. Finding the first object in the 10-to-1 resonance is genuinely significant. It's like finding a new species of animal that people predicted should exist, but had never actually seen before. Now here's where it gets even more interesting. 2020 VN40's orbit is inclined at about 76 degrees relative to the ecliptic plane. That's a massive tilt. Most objects in the solar system orbit roughly in the same flat plane as Earth. They're all within a few degrees of each other. But 2020 VN40 is tilted so steeply that its orbit goes almost straight up from that plane. Imagine a record sitting on a table. Most objects orbit around the center of that record, moving within the plane of the record. 2020 VN40 is orbiting almost perpendicular to that record, like a coin spinning on its edge. And here's what's really bizarre. When 2020 VN40 reaches its closest approach to the Sun, when it's at perihelion, it appears from a top-down view to be approaching the Sun from the same direction as Neptune. In other words, the two objects appear to be on the same side of the solar system at the time of 2020 VN40's closest approach. That's unusual. For most other resonant TNOs, they reach their closest point to the Sun when Neptune is on the opposite side of the solar system. They're in what's called anti-aligned resonance. But 2020 VN40 appears to be in an aligned resonance. Except here's the thing, they're not actually close to each other. They never actually collide or come close to colliding. The reason is that 2020 VN40's orbit is so steeply inclined. From the side view, from the perspective of looking at the solar system from the edge, you can see that while they might appear to be at the same location from a top-down view, the high inclination of 2020 VN40's orbit means they're always well separated in the vertical direction. They're like two dancers who appear to be at the same position when you look from above, but one is on a platform and one is on the ground. They're separated in the third dimension. This unusual configuration is called a novel libration state. Libration is the term astronomers use for the back and forth wobble that occurs when two objects are in orbital resonance. The libration center is the point around which the resonance oscillates. For most resonant objects, the libration is centered at a particular orientation. For 2020 VN40, it appears to be centered in an unusual way that's different from other known resonances. Now the question becomes, how did 2020 VN40 end up in this resonance? How did it get locked into this perfect 10-to-1 dance with Neptune? And how long will it stay there? One possibility is that 2020 VN40 was scattered into its current orbit during the early solar system, when the giant planets were migrating and moving around. During that era, there was chaos. Gravitational interactions between planets could send objects flying all over the place. Some objects got thrown out of the solar system entirely. Some got pulled inward. Others got scattered outward into the distant reaches of the solar system. Maybe 2020 VN40 was one of those objects. Maybe it got scattered into an orbit that brought it into contact with Neptune's gravitational influence. And maybe at that point, Neptune's gravity captured it and locked it into the 10-to-1 resonance. But here's the thing. These resonances aren't permanent forever. They can be destabilized. Gravitational interactions with other objects can knock an object out of resonance. Over enough time, something could disturb 2020 VN40's delicate orbital balance. But according to modeling done by astronomers who studied 2020 VN40, the resonance should be stable for tens of millions of years. So 2020 VN40 is going to stay in this perfect 10-to-1 dance with Neptune for a very long time, at least in astronomical terms. It's not going anywhere anytime soon. But here's what really captures the imagination about 2020 VN40. It's not just an interesting curiosity. It's evidence of something much larger. It's evidence of Neptune's reach. Neptune's gravitational influence extends so far into the solar system that it can lock an object in resonance from 140 AU away. 140 AU, that's 8 times farther than Pluto. That's deeper into the outer solar system than we usually think about objects being influenced by planetary gravity. And yet here is an object, locked in perfect sync with Neptune, separated from it by incomprehensible distances, choreographed by gravity across the void. This tells us something profound about how gravity works. We think of gravity as this force that weakens with distance, and it does. The farther away something is, the weaker the gravitational pull. But gravity is incredibly long-ranged. It reaches everywhere. Nothing in the universe is truly outside of gravity's influence. A massive object like Neptune can exert influences on distant objects, even across 140 AU, and under the right circumstances, those influences can create structures, patterns, synchronized dances that persist for millions of years. 2020 VN40 is also evidence that there are probably other objects out there, in other resonances with Neptune, that we haven't discovered yet. The LIDEO survey has found other objects in the 7-to-1 and 5-to-1 resonances. There might be more out there. As telescopes improve, as surveys become more sensitive and more comprehensive, we're going to find more and more of these distant resonant objects. They're going to help us piece together a picture of what happened in the early solar system and how the planets have influenced the larger orbital structure of the system. And that brings us back to why all of this matters for understanding Neptune. All of these mysteries we've been talking about, the cooling atmosphere, the disappearing storms, the auroras in the wrong place, Triton being a captured dwarf planet with a subsurface ocean, and now 2020 VN40 locked in a perfect cosmic dance. They all paint a picture of a solar system that's far more dynamic and far more complex than we typically give it credit for. Neptune isn't just sitting there at 30 AU minding its own business. Neptune is exerting gravitational influence across vast distances. Neptune is holding captured moons. Neptune is affecting the orbits of distant objects. Neptune is part of an interconnected web of gravitational influences that reaches across the entire solar system. And we're only just beginning to understand the full extent of Neptune's reach and power. Let me be clear about something though. 2020 VN40 isn't the only resonant TNO. There's an entire population of trans-Neptunian objects that are locked in various resonances with Neptune. Some of them are in resonances like 3-to-2, which is Pluto's resonance. Some are in 2-to-5, some in 5-to-2, some in even more complex resonances. But what makes 2020 VN40 special is both that it's in such a high integer resonance and that its resonant state is unusual in how it's oriented. Most other high-resonance objects would be difficult or impossible to find with our current telescopes. 2020 VN40 happened to be in a position where it was discoverable. We got lucky. As our telescopes continue to improve, as surveys like the Vera C. Rubin Observatory come online and start scanning the entire sky repeatedly looking for faint, slow-moving objects, we're going to find more of these distant resonators. We're going to build a more complete picture of what's out there beyond Neptune, and each new object we find is going to teach us something about the dynamics of the outer solar system. This is why 2020 VN40 matters. It's not just a pretty piece of celestial mechanics. It's a messenger from the distant reaches of the solar system. It's telling us that our solar system is far more structured, far more organized, far more influenced by gravitational resonances than we previously realized. It's telling us that planets reach out across vast distances and organize the orbits of objects they'll never directly interact with. It's telling us that the universe operates according to beautiful mathematical principles that we're only just beginning to fully appreciate. And Neptune, that distant ice giant that we've mostly ignored for the last 35 years, is at the center of all of this. Neptune is the orchestrator. Neptune is the one creating the conditions that lock 2020 VN40 into its perfect 10-to-1 dance. Neptune is the source of the gravitational choreography that plays out across 140 AU of space. Neptune is more powerful and more influential than we gave it credit for, but we still haven't answered some of our core mysteries. We still don't know why Neptune's atmosphere is cooling so dramatically. We still don't understand why the auroras are showing up where they shouldn't be. We still can't fully explain the storm systems that appear and disappear. These are questions that will require more observations, more data, more James Webb Telescope time pointed at Neptune and its surrounding environment. And as we gather more data, I suspect we're going to find that all of these mysteries are connected to a deeper story. A story about a planet in the process of changing. A planet with internal dynamics that we've completely underestimated. A planet that has far more to teach us than we ever imagined. Now I want to take you on a journey. I want to take you down through Neptune's atmosphere, down through the clouds, down past the layers of gas, and down into the interior of this planet. Because what's happening inside Neptune, deep beneath the surface, is some of the most exotic physics happening anywhere in our solar system. Let's start at the top. Neptune's atmosphere is about 5 to 10% of the planet's total mass, which means most of Neptune is not atmosphere at all. Most of Neptune is interior. The atmosphere itself extends down for thousands of kilometers, but the pressure increases dramatically as you go deeper. At the very top of the atmosphere, the pressure is low. The temperature is minus 201 degrees Celsius. That's where Voyager 2 took its measurements. That's where Webb is now measuring the dropping temperatures and the auroras. As you go down, though, the pressure increases. The temperature increases. The methane that gives Neptune its blue color becomes more and more abundant in the lower atmosphere. If you were falling downward through Neptune's atmosphere, you wouldn't notice any dramatic change at first. You'd gradually feel increasing pressure. You'd gradually feel increasing heat. But there wouldn't be any sudden boundary, any clear demarcation saying, okay, now you're leaving the atmosphere and entering the interior. Instead, there's a gradual transition. The gases become denser. They become more like a fluid. Eventually, they become so dense and so hot that they're not really gas anymore. There's something in between gas and liquid. The pressure keeps increasing. The temperature keeps increasing. At a certain point, maybe around 100 kilometers below the visible cloud tops, the composition starts to change dramatically. You enter what scientists call the mantle, although it's not like the rocky mantle of Earth. This is an icy mantle, but the word icy is misleading. The ice doesn't exist as solid ice. It exists as a slushy, dense, hot fluid. It's a supercritical fluid, which means it doesn't have a clear boundary between liquid and gas phases. It's something in between. It's plasma-like in some ways. The mantle is composed primarily of water, ammonia, and methane. All of these exist not as solids, but as this hot, dense, slushy mixture. The mantle also has a very important property. It can conduct electricity. It has high electrical conductivity. That's important because Neptune has a magnetic field, and that magnetic field has to be generated somehow. It's generated by the movement of this conducting fluid in the mantle, the same way that Earth's magnetic field is generated by the movement of molten iron in Earth's outer core. The mantle is incredibly thick. It extends down for thousands and thousands of kilometers. The mantle probably contains somewhere between 10 and 15 times the mass of Earth. We're talking about a layer so massive that if you took it and placed it in space by itself, it would make a world about 3 to 5 times the size of Earth. All of this dense, hot, conducting fluid is wrapped around Neptune's core. Now here's where things get genuinely wild. As you go deeper into the mantle, the pressure keeps climbing. At depths of around 7,000 kilometers, the pressure and temperature reach levels that trigger something extraordinary. At those conditions, methane molecules break apart, the carbon and hydrogen separate. The hydrogen is under such extreme pressure that it can recombine into different forms. The carbon, freed from the hydrogen, does something remarkable. It crystallizes. It forms diamonds. This isn't speculative. This isn't theory without any basis. Scientists at Lawrence Livermore National Laboratory have actually created these conditions in the lab. They've subjected methane to pressures and temperatures matching those deep inside Neptune. And they've watched as the methane decomposed and diamonds began to form. The diamonds don't stay at the surface level where they form. They're denser than the surrounding material, so they sink. They fall downward through the mantle toward the core. But as they fall, they're also moving through hot fluid. And eventually, as the pressure and temperature continue to increase, the diamonds encounter conditions so extreme that they too break apart. The diamond crystals dissolve back into carbon. But for a time, for a distance during their descent, there's an actual rain of diamonds falling through Neptune's interior. Try to wrap your head around that. Imagine standing inside Neptune. Imagine looking up and seeing diamonds raining down from above. Not small diamonds, not tiny specks. Real diamonds, potentially the size of hailstones or larger, falling through the hot, dense fluid of the mantle. That's real. That's actually happening inside Neptune right now. But it's even more extreme than that. Some models suggest that even deeper than the diamond rain zone, perhaps at the very top of the region where the water breaks down, there might be an actual ocean, a liquid carbon ocean, with solid diamonds floating in it. Diamonds, those hardest of all substances, those most prized of all gems, drifting through an ocean of liquid carbon, one of the softest of all elements. It's the kind of contradiction that only extreme physics allows. Scientists believe that this diamond rain phenomenon might explain some of the mystery about Neptune's magnetic field. You see, Neptune's magnetic field is generated by currents flowing through conducting material in the mantle. The diamond rain, as diamonds sink through the mantle, might create convection patterns. It might initiate movements and flows in the conducting fluid that generate the magnetic field. The falling diamonds might literally be responsible for some of Neptune's magnetism. It's also possible that the process of diamond formation and sinking plays a role in heating Neptune's interior. When methane breaks apart to form diamonds, energy is released. That energy contributes to heating the surrounding material. Over billions of years, that continuous process of diamond formation could add significant heat to Neptune's interior. Some of that heat radiates outward through the layers and eventually reaches the upper atmosphere. And that might be relevant to something we've been trying to understand. Remember how Neptune's atmosphere is cooling. Remember how the temperatures are dropping hundreds of degrees. One possibility, one hypothesis that some scientists have entertained is that this cooling might be related to changes in how much heat is flowing out from Neptune's interior. If the rate of heat flow from the interior is decreasing, if the rate of energy coming from the core is declining, then the upper atmosphere would cool. The conditions that generate auroras would change. The whole atmospheric dynamic could shift. It's speculative, but it's a possibility worth considering. Below the diamond rain zone, deep in the interior, the pressure becomes even more extreme. The temperature continues to climb. Eventually, you reach the very center of Neptune, Neptune's core. The core is probably composed of rock, iron, nickel, and silicates. It's similar in composition to Earth's core, but much more massive. The core of Neptune is probably about 1.2 times the mass of Earth. So Neptune's core weighs as much as 1.25 Earths. All of that mass is compressed into a relatively small volume. At the very center of Neptune, the pressure reaches what scientists call 7 million bar, or 700 gigapascals. To put that in perspective, that's about 100 billion atmospheres. That's about twice the pressure at the center of Earth. And the temperature at Neptune's core is around 5,000 to 5,400 Kelvin. That's about 5,000 degrees Celsius. That's hotter than the surface of the sun. All of that heat is radiating outward. It's flowing through the layers, through the mantle, through the upper regions of the planet, and some of it makes it all the way to the surface, where it radiates away into space. And here's something important. Neptune is radiating more heat than it receives from the sun. Neptune receives minimal sunlight because it's so far away, but it's actively radiating heat. Where does that heat come from? Some of it comes from gravitational contraction. The planet is slowly compressing under its own weight. As it compresses, it releases energy. Some of it probably comes from radioactive decay of elements in the core, the same process that heats Earth's interior. And some of it might come from chemical reactions happening in the interior, including potentially the formation of diamonds from methane. The fact that Neptune is radiating more heat than it receives from the sun is significant. It means Neptune has an internal energy source. It means the planet isn't dormant. It's active. It's doing things. It's changing. And we've been largely ignoring that fact because Neptune is so far away and so difficult to study. Now, all of this interior structure is held together by one thing: gravity. Neptune's mass is so enormous that its own gravity creates the conditions deep inside the planet. The weight of all the material above pushes down on the material below, creating pressure. At Neptune's center, that pressure is so extreme that it bends space and time itself. The effects are small because Neptune isn't massive enough to create dramatic relativistic effects, but they're there. The fabric of space-time is warped by Neptune's gravitational field. And here's something that really puts things in perspective. Neptune is one of 4 giant planets in our solar system. Jupiter and Saturn are the gas giants. Uranus and Neptune are the ice giants. But the distinction between gas giant and ice giant isn't actually that clear. The divide is somewhat arbitrary. What makes an object an ice giant versus a gas giant is primarily the amount of heavier elements it contains. Ice giants have more heavier elements, more rock and ice and metal in their cores. Gas giants have relatively less. But all four of these giant planets have complex interior structures. All four have cores. All four have thick, dense mantles made of exotic materials. All four have atmospheres on top. All four are active, dynamic worlds with internal heat sources and complex magnetic fields. And Neptune, the smallest of the four giants, the most distant of the four giants, the one we know the least about, turns out to be one of the most interesting. It turns out to be a world with layers of exotic matter, with chemistry and physics that we're only just beginning to understand. It turns out to be a world that's changing, a world whose atmosphere is cooling, whose storms are appearing and disappearing, whose auroras are starting to show up in ways we didn't expect. A world whose magnetic field is tilted and strange and probably connected to diamond rain and liquid carbon oceans deep in its interior. When you think about Neptune, you shouldn't think of it as a dead, frozen, boring world out at the edge of the solar system. You should think of it as an alien planet with wonders happening inside. You should think of it as a place where exotic physics is playing out every single moment. You should think of it as a world that's telling us about the incredible diversity of planets that exist in the universe, both in our own solar system and around distant stars. And that brings us back to James Webb and why its observations of Neptune are so important. Webb is giving us a window into what's happening in Neptune's upper atmosphere. The auroras it's detecting are probably generated by interactions with solar wind and Neptune's magnetic field. The temperature measurements it's taking are telling us about the energy balance in Neptune's upper atmosphere. The data Webb is collecting is going to help us understand what's driving the changes we're seeing, and understanding Neptune's atmospheric dynamics might also help us understand the atmospheres of exoplanets. It might help us learn how to detect signs of life on distant worlds. It might help us build better models of how planets form and evolve. One of the most important realizations from modern astronomy is that every world is unique. There are no two planets alike. Even planets that seem similar in size and distance and composition have different characteristics, different histories, different things going on inside. Neptune is a perfect example of that. It's an ice giant. It's similar to Uranus in many ways, but it's also completely different. Its atmosphere is more active, its storms are fiercer, its auroras are stranger, its magnetic field is more tilted. Its moons are more interesting, especially that captured dwarf planet Triton with its cryovolcanic activity and potential subsurface ocean. Neptune is a reminder that the solar system is far more complex and far more interesting than we typically give it credit for. And it's a reminder that we should continue to explore, continue to observe, continue to ask questions. Because every time we turn a new observatory toward a planet we thought we understood, we find something new. We find something that challenges our models and our assumptions. And that's exactly what's happening with Neptune right now. Neptune has 14 moons, 14 different worlds orbiting in the darkness, held in place by Neptune's gravity. Most of them are small, most of them are barely visible through our telescopes. Most of them don't get a lot of attention from the astronomical community, but collectively, they tell a story about chaos and violence, a story about a system that's been torn apart multiple times and reassembled, a story about a world that continues to be shaped and reshaped by impacts and gravitational interactions. We've already talked about Triton, the captured dwarf planet, the one with the cryovolcanic geysers and the potential subsurface ocean. Triton dominates the moon system. It contains about 99.5% of all the mass that orbits Neptune. All the other moons put together don't add up to 0.5% of Triton's mass. So when you talk about Neptune's moon system, when you talk about Neptune's satellites, you're talking almost entirely about Triton. Everything else is just tiny specks orbiting nearby. But those tiny specks have a story to tell. The most interesting of them, in many ways, is a moon called Proteus. Proteus is Neptune's second largest moon. It's about 418 kilometers across, so it's maybe a third the size of our moon, but still substantial. If you were to visit Proteus, it would actually look quite impressive. It would cover a big chunk of your sky. You could see it changing as you moved across the surface. But Proteus is strange. It's not spherical. It's irregular. It's lumpy and bumpy and battered. And the reason is obvious if you look at images of it. Proteus is covered with impact craters. Big ones, like really big ones. The largest crater is called Pharos, and it's almost large enough to have completely shattered the moon. If the impact that created Pharos had been just a little bit bigger, Proteus might have broken apart. It might have been torn to pieces, but it survived. The impact created this massive crater, but it didn't destroy the moon. When Voyager 2 flew past Neptune in 1989, and sent back images of Proteus. Scientists looked at that crater and thought, okay, so there was a big impact at some point in the past. Interesting. They noted it, they recorded it, they filed it away. They didn't think much more about it at the time. And that would have been that. Proteus would have been a curious but ultimately not that interesting world, a battered old moon that got hit by a comet at some point. Then, in 2013, something changed. A researcher named Mark Showalter from the SETI Institute was looking at archival Hubble Space Telescope images of Neptune from 2009. He was examining images of Neptune's ring system, looking for changes or new structures in the rings. And as he was scanning through the data, he noticed something unexpected. There was a tiny moon orbiting Neptune that nobody had ever documented before. It wasn't in any of the catalogs. It hadn't been mentioned in any of the major surveys. It was just there, a small speck orbiting in the darkness. And apparently nobody had noticed it before. The moon was designated with the technical name S2004N1, but they eventually decided to give it a proper name. They called it Hippocamp, and here's where Hippocamp becomes interesting. Hippocamp is tiny, only about 34 kilometers across. It's about 1,000th the mass of Proteus. It's the smallest of Neptune's known moons. And the most bizarre thing about it is where it orbits. Hippocamp orbits right next to Proteus. They're only about 12,000 kilometers apart. Now that shouldn't be possible. According to gravitational dynamics, a moon the size of Proteus should have cleared its orbital zone. It should have gravitationally swept aside smaller objects. Any tiny moon orbiting that close to a much larger moon should have been pulled in and absorbed. Proteus should have crushed Hippocamp like a fly millions of years ago. So why is Hippocamp still there? Mark Showalter and his colleagues proposed a theory. They looked at that big impact crater on Proteus, the Pharos crater, and they realized that crater could be the key to understanding Hippocamp's existence. They hypothesized that Hippocamp isn't a separate moon that somehow survived orbiting near Proteus. Instead, Hippocamp is a piece of Proteus. It's a fragment that got knocked off during the impact that created the Pharos crater. When the comet hit, it ejected material from Proteus. Most of that material either fell back onto Proteus or drifted away into space, but a chunk of it, maybe the largest chunk that got ejected, remained in orbit. It coalesced. It formed a small moon. That moon is Hippocamp. This was the first time we'd ever found evidence that a moon could be an offshoot from another moon, created by a comet impact. It was exciting. It was a new phenomenon, and it led to an even bigger realization. If Hippocamp came from Proteus, what else might have come from impacts on Neptune's other moons? Researchers started analyzing the data more carefully. They looked at the orbital characteristics of all of Neptune's inner moons, and they realized something that had been hiding in plain sight. Neptune's moon system shows clear signs of being violent and chaotic. The inner moons have characteristics that suggest they've been disrupted multiple times. Some of them have circular orbits when they should have eccentric orbits. Some of them have inclinations that don't quite match what you'd expect. The entire system has the fingerprints of a traumatized environment written all over it. The working theory now is that Triton's capture caused absolute chaos in Neptune's original moon system. When Triton was pulled into orbit around Neptune, it probably scattered the existing moons. It might have ejected some moons entirely from the system. It definitely disrupted the orbits of others. The inner moon system that we see today is probably a second or third generation of moons that reformed after the initial chaos. These reformed moons have been hit by comets and asteroids repeatedly over billions of years. Hippocamp is evidence of that ongoing bombardment. And here's something even more interesting. Hippocamp has a surprisingly circular orbit and a low inclination, given that it's orbiting so close to a much larger moon. Scientists think they've figured out why. Every time Hippocamp gets hit by a comet or an asteroid, it gets disrupted. It breaks apart. The pieces drift apart and eventually reaccrete, coming back together under their mutual gravity. Each disruption event smooths out Hippocamp's orbit. It reduces the eccentricity. It reduces the inclination. Essentially, every time Hippocamp gets destroyed and reforms, it comes back a little bit more circular, a little bit more stable in its orbit. It's been disrupted roughly 9 times in the past 4 billion years. Each time it's come back a bit more refined. It's a strange kind of evolution. Instead of evolving through genetics and natural selection like life on Earth, Hippocamp evolves through catastrophic disruption and reformation. Each impact that destroys it actually improves its orbit. It's like if you could make yourself a better person by getting hit by a car, healing up, and trying again. It's destructive evolution. Now, beyond Proteus and Hippocamp, there are other inner moons. There's Larissa, there's Despina, there's Galatea, and Thalassa, and Naiad. These are all relatively small moons, all of them named after water deities from Greek mythology. They all orbit in relatively regular patterns. They all have relatively circular orbits, but they all show signs of being young surfaces, signs that they've been disrupted or reformed relatively recently. All of them orbit within about 140,000 kilometers of Neptune. That's about a third the distance from Earth to the Moon. And then, farther out, beyond the inner moon system, there are the irregular outer moons, Sao, Laomedea, Neso, and Salmate. These all have eccentric, inclined orbits. They all orbit retrograde or in unusual patterns. They're probably captured objects, similar to Triton, but smaller. And then there's Neso, which is one of the most distant moons of any planet we know of. Neso orbits about 49 million kilometers from Neptune. Its orbital period is about 27 years. Imagine that. A moon that takes 27 Earth years to complete one orbit around its planet. That's an incredibly distant satellite. The reason Neso can orbit so far out is because of something called Neptune's Hill sphere. The Hill sphere is the region around a planet where the planet's gravity is stronger than the gravity of the Sun. Beyond the Hill sphere, the Sun's gravity is strong enough to pull objects away from the planet. Inside the Hill sphere, the planet's gravity dominates. Moons can exist only inside the Hill sphere. Neptune has the largest Hill sphere of any planet in the solar system. Even though Neptune is less massive than Jupiter or Saturn, its Hill sphere is bigger because Neptune is so far away from the Sun. The Sun's gravity weakens with distance. At Neptune's distance, which is 30 AU from the Sun, the Sun's gravity is much weaker than it is near Earth or Jupiter or Saturn. This means Neptune can hold on to moons at much greater distances than the closer planets can. Neptune's Hill sphere extends out to about 117 million kilometers from the center of Neptune. That's enormous. It's larger than the distance between Earth and the Sun, and within this vast sphere of gravitational influence, Neptune holds 14 moons. These moons range from Triton, which is massive and dominates the system, down to Hippocamp, which is tiny and barely holds together against the constant bombardment of impacts. These moons range from inner moons orbiting close and fast, to outer moons like Neso, orbiting so far away that they take decades to complete one orbit. The entire system is a kind of gravitational museum. It's a museum of the history of impacts and disruptions and captures and migrations. It's a museum of violent events happening over billions of years. And it's still being written. Today, as we speak, Neptune's moons are still being impacted by small asteroids. They're still being gradually migrated outward by tidal interactions with Neptune. The system is still evolving. Looking at the moon system teaches us something profound about solar systems in general. We tend to think of planetary systems as being stable and orderly. We think of planets in regular orbits, moons in regular orbits, everything moving in predictable patterns. But the reality is far messier. Solar systems are dynamic. They change. They evolve. They bear the scars of violent events. Neptune's moon system is evidence of that. It's a reminder that the solar system we see today isn't the same solar system that existed 4.5 billion years ago. Planets have migrated. Orbits have changed. Moons have been captured and destroyed and reformed. And that process is ongoing. This is why discovering new moons like Hippocamp is so important. Each new discovery adds another piece to the puzzle. It helps us understand what happened in the past. It helps us build better models of planet and moon formation. It helps us understand exoplanetary systems better. And it reminds us that there's still so much we don't know about our own neighborhood. Standing where we are right now, in this early 21st century, we're in a unique position in human history. We've sent enough spacecraft to distant places that we can see the big picture. We have data from multiple flybys, multiple observations. We can piece together stories like Triton's capture, like the violent early history of Neptune's moon system, like the ongoing impacts that shape the moons today. And we can use these stories to understand worlds far beyond our solar system. We can use what we learn from Neptune to interpret observations of exoplanets. We can use Neptune to learn the language that the universe speaks. Neptune is teaching us to look beyond the surface, to see worlds not as static, finished products, but as dynamic, ever-changing systems. To understand that even worlds we thought we understood completely, worlds we thought were boring and cold and dead at the edge of the solar system, have extraordinary stories to tell if we're willing to listen. Let me ask you something. When's the last time you thought about the changing of seasons? If you live in a temperate climate, you know the feeling. Spring arrives, the temperature warms, plants start growing. Summer comes, it gets hot, then gradually cools. Fall arrives, leaves change color and fall. Winter comes, it gets cold. The cycle repeats. It's one of the fundamental rhythms of life on Earth. It's something we experience every single year. Now imagine if each season lasted 40 years. Imagine if you had to wait 40 years for spring to end and summer to begin. Imagine experiencing 40 years of gradual warming, then 40 years of gradual cooling. That's what Neptune experiences. And we're currently in the middle of one of those extended seasons. We're watching it unfold in real time. Neptune has an axial tilt of 28.3 degrees. That's very close to Earth Earth's tilt of 23.5 degrees. It's also very close to Mars's tilt of 25.2 degrees. So all three of these worlds, Earth, Mars, and Neptune, experience seasons. All three of them have similar reasons for experiencing seasons. Their rotational axes are tilted relative to their orbital planes. As they orbit the Sun, first one hemisphere gets more direct sunlight, then the other hemisphere gets more direct sunlight. This creates seasons. But Neptune's orbital period is 164.8 years. That's the time it takes for Neptune to complete one full orbit around the Sun. This means each season, each quarter of the orbit lasts about 41 years. So when the southern hemisphere of Neptune is experiencing spring, that spring lasts 41 Earth years. That spring began around 2005. And based on the current trajectory, that spring won't end until around 2046. If you're watching Neptune's climate, you're watching a seasonal change that will take a human lifetime to complete. Now here's where things get really interesting. When astronomers started carefully monitoring Neptune's atmosphere using infrared telescopes in the early 2000s, they expected to see a pattern. They expected to see gradual warming as the southern hemisphere moved into spring and then summer. The model was simple. More sunlight arrives, temperatures go up. That's basic thermodynamics. That's what should happen. But the observations told a different story. From 2003 to 2018, astronomers watched as Neptune's globally average stratospheric temperature actually dropped. They saw temperatures fall by about 8 degrees Celsius over 15 years. That's in the opposite direction of what they expected. While the planet should have been warming, it was cooling, and nobody had a good explanation for why. Then between 2018 and 2020, something extraordinary happened. Neptune's south pole suddenly warmed, violently warmed. In just 2 years, temperatures at the south pole jumped by 11 degrees Celsius. That's about 20 degrees Fahrenheit. That's a massive change in a very short time, and it completely reversed the previous cooling trend. The south pole is now the warmest region in Neptune's stratosphere. It's a new polar warm spot, something that scientists had never observed on Neptune before. So we have this contradiction. While global temperatures are cooling, the pole is warming. The pole is warming faster than the equatorial regions. This is backwards from what you'd expect in a simple seasonal model. In Earth's atmosphere, when the sun is more directly overhead at a particular latitude, you get warming at that latitude. The equator is always relatively warm, and the poles are cold. In summer, the pole facing the sun warms up more than the equator does. But it's not because the pole becomes warmer than the equator. It's warmer relative to what it normally is, but the equator is still the warmest region. On Neptune, though, the pattern is reversed. The pole is becoming the warmest region, and it's doing so even while global temperatures are cooling. This suggests that something is going on in Neptune's atmosphere that we don't fully understand. Something is changing the distribution of heat in ways that violate our expectations. Scientists have proposed several theories. One involves the chemistry of Neptune's atmosphere. Neptune's atmosphere is mostly hydrogen and helium, but there's a small amount of methane, maybe 2%. Methane absorbs sunlight very efficiently. When sunlight hits methane molecules, the methane absorbs the energy, and that heats the atmosphere. As more sunlight reaches Neptune during its spring and summer, you'd expect more methane to absorb more light, leading to warming. But here's the twist. Ultraviolet light from the sun can break apart methane molecules. When a methane molecule gets hit by a UV photon, it splits. The carbon and hydrogen separate. They recombine into other hydrocarbons, primarily ethane and other larger organic molecules. These new hydrocarbons have different properties than methane. They don't absorb sunlight efficiently. Instead, they radiate heat very effectively. They're very good at cooling the atmosphere. So as spring and summer progress, two opposing effects are happening. One, there's increased direct sunlight, which heats the atmosphere through methane absorption. Two, there's increased UV light, which breaks apart methane and creates ethane, which cools the atmosphere. If the cooling effect is stronger than the heating effect, the net result would be cooling, and that's potentially what we're seeing. But this doesn't explain the rapid pole warming. So scientists have proposed another mechanism. They think the pole warming might be related to atmospheric dynamics. As the atmospheric temperature distribution changes, winds shift. The structure of the atmosphere changes, and this could create conditions where warm air concentrates at the pole. It's similar to processes in Earth's atmosphere where polar vortices form, concentrating either warm or cold air at the poles depending on various atmospheric conditions. The problem is, we don't have enough data to confirm these theories. We've only been monitoring Neptune intensively for about 20 years. That's only about half of a single Neptunian season. Scientists don't know whether the cooling and the pole warming are normal parts of Neptune's seasonal cycle, or if they represent something unusual. They don't know if the polar warm spot will persist, or if it will fade. They can't see the full pattern because they don't have enough time data. This is where James Webb Space Telescope becomes incredibly valuable. Webb is now monitoring Neptune's stratosphere regularly. It's taking measurements of temperature and composition. It's observing how the auroras change. Over the next decade or more, as Webb continues to observe Neptune, We're going to build up a longer time series of data. We're going to see how the seasons actually evolve. We're going to test these theories. We're going to figure out whether the cooling trend continues, whether the polar warming persists, whether there are other surprises waiting for us. And here's something else to consider. The seasonal changes on Neptune aren't just atmospheric phenomena. They're connected to what's happening on Neptune's moons. Triton, for instance, also experiences seasons. Since Triton is tidally locked to Neptune, it doesn't rotate relative to Neptune. One side always faces Neptune, the other side always faces away. But as Neptune orbits the sunlight hitting Triton changes. Triton's seasons are tied to Neptune's seasons. Neptune is currently in its southern summer, which means Triton's south pole is experiencing summer too. As Triton's south pole experiences summer and gets more sunlight, the temperature increases. Frozen nitrogen and methane on Triton's surface begin to sublime, turning into gas. This creates an atmosphere. Triton has an atmosphere right now, something that's only possible because it's summer. In winter, all the atmospheric gases would freeze back onto the surface. So Triton's seasons are literally creating and destroying an atmosphere. The atmosphere waxes and wanes with the seasons. This atmospheric cycling on Triton is probably exchanging material between the surface and the potential subsurface ocean. As the atmosphere forms and dissolves, as gases escape and condense, there's probably some interaction with the cryovolcanic activity happening beneath the surface. The seasonal changes on Neptune are driving seasonal changes on Triton, which are affecting the entire Triton system. Now think about what this means for understanding planetary climate. On Earth, we worry about seasonal changes that happen on a timescale of months. We worry about climate change that happens on a timescale of decades. We study phenomena like El Niño cycles that repeat on timescales of years. Neptune teaches us to think about time on vastly larger scales. Neptune teaches us that a planetary atmosphere can take decades to respond to seasonal changes, that a heating event can take years to fully develop, that a planetary system can exhibit behaviors that take longer than a human lifetime to fully manifest. This has implications for how we think about climate on exoplanets. When astronomers observe distant planets around other stars, they can only get snapshots of those planets, maybe one observation, maybe a few observations. They can't monitor a planet over decades. They can't watch seasonal changes unfold. But by studying Neptune, by learning how Neptune's atmosphere responds to seasonal forcing, by understanding the timescales involved, we can build better models for interpreting exoplanet observations. We can extrapolate from what we see in a single observation to understand what might be happening over longer timescales. Neptune is teaching us that planetary atmospheres are far more complex and far more dynamic than we initially understood. Neptune is showing us that simple models of how sunlight heats an atmosphere don't fully capture what's actually happening. Neptune is forcing us to think about chemistry and atmospheric dynamics and the interaction between different physical processes. And Neptune is showing us that getting good science requires patience. It requires long-term monitoring. It requires collecting data over many years so you can see patterns emerge. And we're only now entering the era where we have the tools to really monitor Neptune continuously. The era where we can turn telescopes like WEBB toward Neptune and keep watching, collecting data year after year. The era where we can finally begin to understand the patterns that are unfolding in Neptune's atmosphere. We're at the beginning of a new chapter of Neptune science. We're finally ready to pay attention to this distant world in the way it deserves. The seasonal changes on Neptune are a reminder that every world is unique. Every world has its own rhythms, its own patterns, its own way of responding to the energy it receives from its star. And understanding those rhythms requires observation, requires patience, requires the commitment to keep watching even when the changes happen on timescales that dwarf human lifespans. Neptune is teaching us to think bigger, to think longer, to expand our understanding of time itself. Let's talk about the future. Let's talk about what happens next. Because right now, as we're watching Neptune reveal its secrets through the lens of the James Webb Space Telescope, there are people on Earth making plans. Plans to go back to Neptune, plans to send a spacecraft there, plans that could change everything we understand about this distant world. The reality is sobering. Since Voyager 2 flew past Neptune in 1989, no other spacecraft has visited. That's 36 years of Neptune being observed only through telescopes, 36 years of studying the planet from a distance, 36 years during which we've made enormous advances in spacecraft technology, in our understanding of planetary science, in the instruments we can build, and yet we haven't sent anything new to Neptune. We haven't sent anything new to any of the ice giants. While we've been studying Mars intensively with rovers and orbiters, while we've been planning missions to Europa and Enceladus, the ice giants have been neglected. But that's starting to change. There's a proposal on the table, a serious, detailed, well-thought-out proposal. Chinese scientists have proposed a Neptune orbiter mission. They're calling for a launch window around 2033. If approved and funded, this spacecraft would launch from Earth in 2033 and would arrive at Neptune in 2049. It would take 16 years to get there, using gravity-assist flybys of Jupiter and Saturn to accelerate the spacecraft and reach Neptune with the right velocity to enter orbit. Upon arrival at Neptune, the Chinese spacecraft would do something extraordinary. It would release an atmospheric probe directly into Neptune's atmosphere. This probe would descend through the clouds, taking measurements as it goes. It would measure temperature, pressure, wind speed, composition. It would radio data back to the orbiter as it descends, and then, after it gets too deep for radio signals to be received, after it's destroyed by pressure and heat in the depths, the orbiter would perform a gravity assist maneuver at Triton. It would use Triton's gravity to slow down and enter a stable orbit around Neptune. From that orbital position, it would spend years studying the Neptune system, studying the planet, studying the moons, studying the ring system. The orbiter would be equipped with 11 scientific instruments: magnetometers to study the magnetic field, particle analyzers to study the interaction with the solar wind, dust analyzers to study the particle environment, multiple spectrometers to study light at different wavelengths, a camera to take images, a microwave radiometer to study the interior of the planet, navigation systems, all of this powered by 2 radioisotope thermal generators, which convert the heat from radioactive decay into electricity. These RTGs are essential for missions so far from the Sun. Solar panels would be useless at Neptune. The Sun is too dim. RTGs are the only practical power source. This is a real proposal. It's been presented to the Chinese space authorities. It's being seriously considered as part of China's deep space exploration program. According to some sources, the intended launch date is around 2033 or 2035, following a Chinese Jupiter mission that would launch earlier. If this mission is approved and funded, we would finally break the drought. We would finally send something new to Neptune. We would finally gather the data we desperately need to answer the questions that have been plaguing us. But here's the thing that's frustrating, at least from the perspective of the broader space exploration community. NASA was supposed to be leading this effort. NASA has been considering Neptune missions for years. Scientists have written white papers. They've made proposals. They've advocated for a flagship-class mission to the Neptune Triton system. The argument for this mission is compelling. We know less about Neptune than about any other planet in the solar system. Neptune is home to some of the most extreme physics and chemistry happening anywhere. Neptune's moon Triton might have life. The scientific case is strong, and yet NASA hasn't funded it. NASA hasn't committed to it. The reasons are complicated. Mostly it's money. Deep space missions are expensive. A Neptune orbiter would cost somewhere in the range of $2 to $3 billion. That's not cheap. NASA's budget has been under pressure. There have been competing priorities: Mars missions, lunar missions, missions to the icy moons of Jupiter and Saturn, Europa Clipper, Juno, InSight. All of these missions consume resources, and in the competition for funding, Neptune has been left behind. There's a political element to this too. Neptune is far away. There's no plan to send humans there. There's no near-term plan to return samples to Earth. There's no clear connection to human exploration or to resource utilization. It's pure science. It's knowledge for knowledge's sake. And while that's valuable, it's hard to justify to government funding agencies when there are other priorities that seem more tangible. But now China is stepping up. China is saying, we'll do this. We'll send a spacecraft to Neptune. We'll gather the data. We'll learn what Neptune can teach us. And suddenly the calculus changes. Suddenly there's a geopolitical element. If China sends a spacecraft to Neptune and NASA hasn't, NASA falls behind. The United States loses scientific leadership in an important area of solar system exploration. This could be the catalyst that makes NASA finally commit to a Neptune mission, or it could lead to an international collaboration with NASA and other space agencies partnering with China to send a joint mission. That's happened before. The International Space Station is a joint project of multiple countries. Robotic missions have involved international partnerships. What would a comprehensive Neptune mission look like? If NASA and ESO and other space agencies decided to commit to a serious mission to Neptune, what would they prioritize? What would they want to know? First, they'd want a comprehensive understanding of Neptune's interior. They'd want to measure the planet's magnetic field in detail. They'd want to study how the magnetic field is generated. They'd want to test theories about the diamond rain and the liquid carbon ocean. They'd want to use seismic instruments to study the interior structure, similar to how we study Earth's interior using seismic waves from earthquakes. They could send sound waves into Neptune's atmosphere and measure how they bounce around and reflect. That would tell them about the internal density structure. Second, they'd want to study Neptune's atmosphere in unprecedented detail. They'd want continuous monitoring of temperature, pressure, wind speed, and composition. They'd want to understand the storm systems. They'd want to figure out why the temperature is cooling. They'd want to understand the auroras. The atmospheric probe would be crucial for this. As it descends through the atmosphere, taking measurements all the way down, it would provide a detailed profile of atmospheric conditions from the top to deep inside. Third, they'd want to study Triton exhaustively. They'd want high-resolution images of the surface. They'd want to map the cryovolcanic activity. They'd want to search for evidence of geysers currently active. They'd want to measure the gravity field around Triton to infer things about the internal structure. They'd want to detect the magnetic field if it exists. Most importantly, they'd want to study whether there's an ocean underneath. They'd want to figure out if there are conditions suitable for life. Fourth, they'd want to study the other moons, Proteus and Hippocamp and all the others. They'd want to map the moon system. They'd want to understand how these moons formed and how they've evolved. They'd want to answer the question of whether Hippocamp's origin story is repeated elsewhere in the system. Fifth, they'd want to study the ring system. They'd want to understand the ring arcs. They'd want to figure out what's happening to them, whether they're stable or changing. They'd want to study the shepherding effects of the moons. They'd want to gather enough data to develop a complete model of how the Neptune ring system works. Sixth, they'd want to study the radiation environment. They'd want to measure how the solar wind interacts with Neptune's magnetosphere. They'd want to understand the particle environment. They'd want to trace the connection between solar wind input and atmospheric processes. A mission that did all of this would be transformative. It would answer questions we've had for decades. It would solve mysteries that have puzzled scientists, and it would raise new questions. It always does. Every time we send a spacecraft to a new place, we learn things we didn't expect. We see phenomena we didn't anticipate, and those new discoveries drive the next wave of exploration. But here's what really excites me about the possibility of a new Neptune mission. It's not just about Neptune, it's about what this mission would tell us about worlds throughout the universe. Neptune is one of an entire class of planets called ice giants, or sub-Neptunes. These planets are incredibly common throughout the galaxy. When astronomers look at exoplanetary systems around distant stars, they find more planets in the Neptune mass range than in any other mass range. There are more sub-Neptunes and ice giants around other stars than there are Earth-sized planets or giant planets. And we barely understand how these planets work. We understand gas giants because we have Jupiter and Saturn to study. We understand rocky planets because we have Earth and Mars. But ice giants? We have two examples, Uranus and Neptune, and we've barely studied them. We have no detailed understanding of their interiors, their atmospheres, their magnetic fields, and yet understanding ice giants is crucial for understanding planetary diversity throughout the universe. When we study an exoplanet around a distant star, and we determine that it's probably in the ice giant mass range, we don't know what to expect. We don't have a good model. We don't know if it should have the same characteristics as Neptune or different characteristics. By studying Neptune in detail, by sending a comprehensive mission there, we would establish what Neptune-class planets typically look like. We would create a reference standard, and that reference standard would help us interpret observations of exoplanets. It would help us figure out what those distant worlds might be like. It might help us identify which of them are potentially habitable. So a Neptune mission isn't just about satisfying scientific curiosity about one distant planet. It's about understanding an entire class of planets. It's about learning lessons that apply throughout the galaxy. It's about preparing ourselves to understand the universe as we detect and study more exoplanetary systems. And there's one more angle worth considering. Triton, specifically. Triton is the most interesting place in Neptune's system to look for life. If there is life on Triton in the subsurface ocean, it would be the second place in our solar system where we've found life outside Earth, and that would fundamentally change how we understand life. It would tell us that life arose independently in at least two places. It would suggest that life is abundant throughout the solar system, that there might be life on Europa, on Enceladus, on other worlds. It would reshape our entire understanding of our cosmic neighborhood. Finding life on Triton wouldn't answer all of life's big questions, but it would answer one of the most fundamental ones. It would tell us that we're not alone, that life isn't some cosmic accident limited to one planet, that the universe is fundamentally different from how we imagined. That's why a Neptune mission matters. That's why we should be excited about the prospect of a Chinese spacecraft heading to Neptune in 2033 and arriving in 2049. That's why NASA should consider investing in its own Neptune mission, because Neptune is calling. Neptune has secrets to tell, and we're finally ready to listen. We started this journey with a question. We started by looking at 4 mysteries that came from the images the James Webb Space Telescope sent back from Neptune, a planet that was cooling when it should be warming, auroras appearing where they shouldn't be visible, a mysterious object locked in a perfect cosmic dance, and a moon system that seems designed to harbor life. We asked, what does this all mean? How do these pieces fit together? And now, after traveling through 2 hours of exploration, after descending into Neptune's interior, after meeting Triton, and understanding its violent capture. After studying the orbits of distant trans-Neptunian objects, after learning about rings and moons and seasons, I think we have enough perspective to attempt an answer. Neptune isn't a static world. Neptune isn't a dead planet. Neptune is alive. Not alive in the way we think of life on Earth, not alive in the sense of organisms and ecosystems, but alive in the sense that it's dynamic, it's changing, it's evolving. It's a system where processes are happening right now, where the atmosphere is responding to seasonal changes on a timescale of decades, where storms are forming and dissolving, where heat is flowing from the interior, where gravitational forces are sculpting the system around it. Neptune is a world in the middle of a story that started billions of years ago with the capture of Triton and the violent disruption of the moon system. A story that continues today with the temperature changes and the Aurora discoveries. A story that will continue into the future with the orbital migrations and the seasonal cycles and the ongoing impacts from comets and asteroids. And we're privileged to be alive at a moment in human history when we can finally see this story. We're privileged to have telescopes powerful enough to observe Neptune from billions of kilometers away. We're privileged to have scientists willing to dedicate their careers to understanding this distant world. We're privileged to have spacecraft that have actually visited Neptune and sent back detailed information. We're privileged to have the James Webb Space Telescope operational and pointing at Neptune, revealing things we never could have seen before. Let's go back to where we started. Let's revisit those 4 mysteries with everything we now know. The cooling atmosphere. We talked about how Neptune's upper atmosphere has cooled hundreds of degrees over the last 35 years. We talked about how this violates our simple models of planetary heating. But what if the cooling isn't a violation of planetary science? What if it's telling us something important about how ice giant atmospheres actually work? What if the cooling is the planet responding to something happening in its interior? What if the internal heat output is changing? What if processes deep inside Neptune, the diamond formation, the chemistry of the mantle, the radioactive decay, all of these are fluctuating in ways we don't yet understand? The cooling atmosphere might be a window into Neptune's interior. It might be the planet's way of telling us that something fundamental is changing in its structure. The Auroras in the wrong place. We talked about how Neptune's magnetic field is tilted at 47 degrees. We talked about how this causes auroras to form at the mid-latitudes instead of the poles. But why is the magnetic field tilted in the first place? We still don't have a complete answer. But we know it's connected to how the magnetic field is generated, probably in the conducting liquid layer of the mantle. And that brings us back to the interior. The interior structure is creating an unusual magnetic field configuration. The magnetic field is creating unusual auroras. Everything traces back to the fact that Neptune's interior is weird. Neptune's interior is different from what we expected. Neptune is teaching us that we don't fully understand how ice giant interiors work. The perfect 10-to-1 resonance of 2020 VN40. We talked about how this tiny object is locked in a cosmic dance with Neptune. We talked about how this demonstrates the long reach of Neptune's gravity. But it also demonstrates something else. It demonstrates that Neptune's gravitational influence extends far beyond where we typically think planets have influence. It demonstrates that the solar system is more interconnected than we imagined. Objects at 140 AU are still significantly influenced by a planet at 30 AU. Gravity doesn't switch off, it reaches everywhere. And Neptune is reaching out across the void and choreographing the orbits of distant objects. Triton and the potential subsurface ocean. We talked about how Triton was captured by Neptune, about how it's geologically active, about how it probably has an ocean beneath the ice. We talked about how that ocean might harbor life. And if Triton does have life, it changes everything. It changes our understanding of where life can exist. It changes our understanding of the abundance of life in the universe. But even if there's no life on Triton, the existence of the subsurface ocean alone is significant. It's significant because it shows that worlds far from the sun can still have internal energy and internal activity. It's significant because it shows that being frozen doesn't mean being dead. Triton is potentially alive in the most interesting sense, the sense where chemical energy drives biological processes in the darkness beneath the ice. These 4 mysteries are connected. They're all expressing different aspects of the same fundamental truth. Neptune is more complex than we thought. Neptune's interior is stranger than we imagined. Neptune's magnetic field is unusual. Neptune's moon system is violent and dynamic. Neptune's atmosphere is changing. Neptune is a world that challenges our assumptions. Neptune is a world that's forcing us to revise our models and our understanding. And here's what really matters. Neptune isn't unique in this regard. Neptune is just the nearest example of an entire class of planets. Ice giants exist around countless other stars. When astronomers observe exoplanetary systems, They find ice giants in many of them. Some of those ice giants might be closer to their stars than Neptune is to our sun, receiving more heat. Some might be farther out, but all of them are probably experiencing their own versions of the phenomena we observe on Neptune. All of them probably have complex interiors. All of them probably have unusual magnetic fields and strange auroras. All of them probably have moon systems with stories to tell. By studying Neptune, by understanding Neptune, we're gaining insights that will help us understand planets throughout the universe. And that brings us to the last thing I want to address, the question of why this matters. Why should you care about Neptune? Why should any of us care about a distant ice giant that we can't even see with our naked eyes? Why should this matter to anyone other than professional astronomers? Here's why. Because Neptune is a mirror. Neptune is a place where we can see how the universe actually works, stripped away from the complications of life, stripped away from the atmosphere of Earth, stripped away from all the noise and chaos of our own world. Neptune is fundamentally honest. It's not hiding anything. It's just being what it is. And what it is strange. What it is complex. What it is worthy of our attention. And more than that, Neptune is humbling. Neptune is a reminder that for all the progress we've made in science, for all the knowledge we've accumulated, there are still vast regions of our own solar system that we barely understand. There are still planets orbiting our own sun about which we have profound ignorance. There are still mysteries waiting to be solved, and those mysteries are right here, within reach, in our cosmic neighborhood. We don't have to wait for distant telescopes observing alien planets to find wonders. We have them right here. Neptune is proof that there's still so much to discover. There's still so much to learn. That matters. In a world where we sometimes feel like science has answered all the big questions, where we sometimes feel like we've understood everything important, Neptune reminds us that we haven't. Neptune reminds us that exploration matters, discovery matters, curiosity matters. There are still blank spaces on our map. There are still mysteries to solve. And maybe that's the most important thing about Neptune. Maybe the most important aspect of Neptune's current mysteries isn't any single discovery we might make. Maybe it's the reminder that the universe is bigger and stranger and more wonderful than we typically give it credit for. Maybe it's the reminder that we should keep asking questions. We should keep exploring. We should keep pointing our telescopes at distant worlds and asking, what's going on there? What can you teach us? So here's where we stand. The James Webb Space Telescope has revealed new auroras on Neptune. It's revealed a temperature drop that nobody can fully explain. It's revealed that Neptune is more complex than we thought. And in response, people are making plans. China is proposing a Neptune mission. Scientists around the world are making detailed observations. Researchers are developing new theories and new models. The scientific community is paying attention to Neptune in ways it hasn't for decades. And maybe in the next 15 or 20 years, we'll send a spacecraft to Neptune. Maybe we'll orbit the planet and take detailed measurements. Maybe we'll send a probe into the atmosphere. Maybe we'll study Triton in detail. Maybe we'll finally answer the questions that have been plaguing us. Maybe we'll finally understand the cooling atmosphere, understand the auroras, understand the entire Neptune system. Or maybe we won't. Maybe budget constraints will persist. Maybe other missions will take priority. Maybe Neptune will remain a mystery for another generation. But the fact that we're asking the questions, the fact that we're trying to understand, the fact that we're dedicating resources and effort to exploring this distant world, that matters. That's what exploration and science are fundamentally about. Let me ask you something before we end. Think about where Neptune is right now. Think about 4.5 billion kilometers from the sun. Think about a world so distant that sunlight takes over 4 hours to reach it. Think about a world so cold that every chemical you can imagine is frozen solid. Think about a moon that orbits that world backwards, a moon that shouldn't be there, a moon that was captured from somewhere else billions of years ago. Think about the geysers erupting from that moon's frozen surface. Think about the ocean that might exist beneath the ice. Think about the possibility that life might be present in that ocean, powered by chemical energy from hydrothermal vents, thriving in the darkness. Now think about the fact that we know all this. Think about the fact that humanity, sitting on a small rocky planet orbiting an ordinary star, has managed to figure all this out. We've looked across the void of space. We've used mathematics and physics and chemistry and engineering to understand what's happening billions of kilometers away. We've sent spacecraft to visit distant worlds. We've built telescopes powerful enough to see those worlds in detail. We've dedicated careers and institutions to trying to understand the universe. And it's worked. We've learned things. We've made discoveries. We've expanded our understanding. That's remarkable. That's worth celebrating. That's worth being excited about. Neptune is a reminder of that remarkable capacity we have, our capacity to wonder, our capacity to ask questions, our capacity to explore, our capacity to build tools that let us see farther and understand deeper. Neptune is out there, still mysteries within mysteries, still questions without answers, still holding secrets. And we're pursuing those secrets. We're trying to solve those mysteries. We're trying to understand. Now, I need to ask you something. You've spent the last 2 hours with me exploring Neptune. You've learned about its atmosphere and its interior and its moons and its rings. You've learned about mysteries that are still being solved. You've learned about plans for future exploration. And hopefully you've caught some of the excitement. Hopefully you've felt some of the wonder. Hopefully Neptune has become more real to you, more interesting, more worthy of your attention. If that's the case, I have a favor to ask. Subscribe to this channel. Hit that subscribe button, because we're going to continue exploring the solar system. We're going to continue looking at distant worlds and trying to understand them. We're going to continue asking questions. And if you subscribe, you'll be part of that journey. You'll get to see what we discover next. But more than that, I want to hear from you. Comment below. Tell me what you think about Neptune. Tell me whether you think we should send a mission there. Tell me what you think about the possibility of life on Triton. Tell me what aspect of Neptune fascinated you the most. Tell me what questions you still have. The comments section is where we have conversations. It's where you get to be part of the exploration community. It's where you get to contribute your ideas and your thoughts. And if you really want to support this kind of content, consider supporting the channel through Patreon or through other means. Scientific exploration costs money. Television production costs money. We do this because we believe in it. We believe that understanding the universe matters. We believe that sharing that understanding with people matters. Your support makes it possible for us to continue doing this work. Neptune is waiting. Neptune has been waiting for 36 years since Voyager 2 flew past. Neptune has been waiting for us to turn our attention back to it. Neptune has mysteries to share. Neptune has lessons to teach. And we're finally listening. We're finally paying attention. The age of Neptune exploration is beginning again. I'm excited about what we're going to discover. I'm excited about what future missions might reveal. I'm excited about the possibility that life might be found on Triton. I'm excited about all of it. And I hope you're excited too. Thank you for taking this journey with me. Thank you for spending 2 hours exploring a distant world with me. Thank you for your attention and your curiosity. Neptune is out there, still mysterious, still wonderful, still calling to us. And as long as we keep listening, as long as we keep asking questions, as long as we keep exploring, Neptune will continue to teach us. Neptune will continue to reveal its secrets, and we will continue to understand our universe a little bit better. Keep looking up. Keep wondering, keep exploring, because the universe is far bigger and far stranger than we imagine, and there's so much more to discover.